Excellent. So after I now fulfilled my duty of ringing the bell, I'd like to welcome you for day 4 of this workshop. I have the big pleasure to introduce David Koch with his talk. I met David years ago in Zurich, and I got always slightly confused about his career. So I got to know him as someone who is a kind of a hardware tinkerer, building NCR and builds like full-scale systems. And then we chatted and I learned he did formal verification. I mean, now he's at a startup as well. I'm super excited to hear what you're doing. And yeah, it's really interesting to see several careers in a single person. So,
no, thank you very much for the introduction, Tobias. And yes, I'm always slightly confused about my own career. And some of that is the topic of what I'm going to talk to you about. So I had presented this as my title because this is a rough description of what I've been attempting to do for a little while. But given Peter's suggestion the other day to talk about the sort of the social aspects and perhaps the interplay with testing and other things, what I thought I would do is something a little bit unconventional and effectively give a few examples from things I've worked on over the last 10 years or so. And where I have spent a lot of that time, I effectively embedded myself into a systems group as sort of an agent, and hopefully an agent of change in spreading the message of formal methods. And so what I thought I would do is take a couple of examples of things that worked and why I think they worked, and things which very much didn't, and why I think they failed. And some of that is my fault, and I aim to own my mistakes, such that hopefully anybody else might profit by learning from them. So my personal, hello, this worked a moment ago. Something from Dell flicked up on my laptop. This is not a Dell laptop. It said, do I want to install a Dell peripheral manager? I said no. And then the clicker stopped working. There we go. Now we're back. All right. So my prehistory is that I began in research in both systems and formal methods at the same time as a member of the SEL4 project, where we wrote and verified a microkernel. I'm not going to bore you with the details of that today because it's not really relevant, except that one of the parts in that project which always frustrated me the most was the very simplistic nature of the machine model that we ended up adopting, which in that project was called the machine monad, because the thing was written in Haskell originally, and so it's a monad. And so the model that SEL4, so the verified microkernel, actually has of the machine it's running on is in reality very, very simple. Right? The state of the kernel itself is modeled very precisely. There's a flat area of bytes with a very clever lifting into C-typed heaps that allow the verification to proceed. So exactly what the kernel does to its own state is quite precise, but its model of the rest of the machine is exceptionally vague. Certain things, like memory that it explicitly writes to in a user-level process, is modeled, but other than that, the only thing it says is that there is this series of machine operations, and these are things like TLB invalidates, cache flushes, barriers, and the only thing the proof actually says is that the sequence of operations that's listed in the abstract specification is exactly the sequence that the C code produces. That's what the proof says, but it says nothing about whether those are the correct operations or have the correct effect on the hardware. This always bugged me, and this sort of drove me to see whether we could I could try and get a bit more precision in here. And so I ended up interacting with a lot of the work that's being done more recently in modeling machines more accurately. So the first of the three pieces of work I wanted to look back on was what I called decoding nets. So where this started was from an observation, and a lot of the slides I'm going to show you today are the original slides from when I or a student presented this work. So they are, to some extent, a historical artifact that I'm critiquing for you. In many cases, I stand by what they say, but in many cases, I don't, and I will point that out where I've realized that we had better ideas since. So where this started was from working on really quite small computers. I started, when I first moved to ETH, I worked on the Barrelfish operating system, which, for anybody who's not familiar with it, uses something like an SEL4 microkernel, replicates it across many, many cores and different cores, and then tries to synthesize a whole machine up above it. And it was always very interested in tackling the hardware head-on, full complexities, right? And in particular, this model of what memory might look like, where your cores look onto a big shared address space, and maybe you've got a DMA device down in there, which is talking directly into DRAM, right, is hopelessly inadequate. So this diagram, somewhat annotated, is for a quite old SoC that was popular in mobile phones 15 odd years ago. This is what the interconnect in that quite simple chip. This has 2 Cortex A9s. This is much, much more simple than the chip is in your phone today. And all of these are different address spaces, and they really are quite different. There are other cores over here. Little M3 cores over here, A9 cores, a DSP, and there are several others hiding in there. And these all things all have quite a different view of what the address space looks like. For example, there is this GPT-5. This is a timer peripheral. So to begin with, from one of the A9, the application cores, this thing appears twice. This is a shorthand I came up with for expressing this stuff at one point that the students decided they really liked and they kept using. What this is this address plus that many zeros at the end. Okay? So one way to get to it is you go down to the regular interconnect, the thing that's really pretending to be physical addresses, and it's mapped in here at this address. Alternatively, for some reason, it has a private access to this peripheral, so it appears at a second address. As I said, there are multiple other cores on this machine. There's a DSP. This DSP also has a private interface to this thing, but at a different address. It shares, however, the same mapping of it through this L3 interconnect. These M3 cores over on the side here, however, only see it through the L3 interconnect, but again at a completely different address because there's additional remapping hardware in here, which is changing the addresses this thing sees. Right, so this is all fun, and you can sort of try to write this down. The even funner part is that a lot of these translations in here are configurable. The manufacturers put in these bits of hardware that let you swizzle all these bits around. And there are layers of firmware down there which are actually responsible for doing that. And they need to do this correctly, otherwise everything falls in a heap. So we were not attempting to sort of solve the whole problem in one go. But what I tried to do myself was to see whether I could come up with a description of some of what's going on. Something that I was confident was formally complete, right? I could reason about, but was simple enough that I could actually get an engineer to adopt it. Which, for anybody who's sort of attempted this, and a number of people have talked about doing this, is a delicate balancing act, and this is a social exercise, right? So what I settled on at one point was just to make something extremely simple. You have a whole network of address spaces. Within each address spaces, I called them nodes. Any given input address is either accepted, so it stops here, that resource lives here, or it's mapped onto another node at a different address. There is some set brackets down here. These were for some non-determinism because the model supports refinements. Okay, and this was it. This is to try to write it down extremely simple. And is this enough to talk about the hardware? actually, sorry, first, the formalism. I forgot this was in here, sorry. We went and did some actual work on the formalism. Yes, you can view it as a relation. There's got a little operational semantics. If you pretend you're like a page table walker, things. You show that these things are equivalent. And this is all the fun formal method stuff, which, I could amuse myself with by going and showing is correct. Was it necessary? One question I used to get was, well, is it actually necessary to have this fully connected graph, right? Is it really that complex? And the answer was, well, yeah, in that piece of hardware I started by showing you, we were actually able to configure this such that the resolution of an address that you issued on a CPU actually passed through the network and went through the same address space twice at different locations. We never actually managed to force a bit of hardware to loop in resolving a physical address, but I'm convinced it will be possible somewhere, right? Just looking at the complexity of these things. And so you did actually have to show termination for these things. And this is just you have issued a physical address where most models, including the SL4 model very much, is assuming, okay, now you have a unique, name for this physical resource, right? And everybody agrees on what it is. And this is just very, very much not true. It is an absolute nightmare down there. Okay, this was, yes, you've got some equivalence. You define an equivalence relation. Yes?
In situations where you find this kind of ridiculous complexity,
yes.
There are often good reasons and bad reasons why things are so complex.
Yep.
Do you have a sense of what the good reasons are here?
Good reasons. So, I mean, yes, I'm always primed to talk about the bad reasons, and they are that generally it's because people have cut and pasted things together and just put a layer of glue between them. I mean, to some extent, the good reasons are that this is an organizationally very complex problem, right? You have the people who are building these SoCs they're not doing this to be difficult, right? And they are very clever people. They know what they're doing, but they are trying to tackle a very hard problem, and which is that they have these completely different pieces of hardware that they've been instructed need to go into this chip. And they need to make them work together somehow. And as far as I can see, what's happening is that they're taking the tool that is available to them, right? They are not given the ability to modify any of the behavior inside, the A9 core, right? Or the DSP, or even the caches and things are already specified. They're already IPs that they're just integrating. The only place they can reach in and make a change is by, flipping around physical address bits. And so that's where they do it. And to some extent, another thing that they're trying to satisfy is that they want, at least the way these things are designed is that you want, say, Android running on those A9 cores to think it's the real operating system, right? Because it's Linux, it thinks it runs the world, right? But you've got something else running over on these other cores, which say, no, I'm the real operating system, right? I actually know where the DSP is that's doing the baseband stack. And for regulatory reasons, I've got to split this off from that. So what do? I give you a little thing where you can, make these addresses disappear for that side. That's sort of my best answer, I think, for the good reasons without being able to read minds. So, yes, on the formal side, you define a nice equivalence relation where you break up blocks that were otherwise going to the same place, and you show that two address spaces, two views from different nodes are equivalent. The same input address always resolves the same output address. Yes, Peter.
Continuing that line.
Yes.
This is kind of a bit complicated.
Yes.
Not super complicated.
No.
I wonder what your sense is of what fraction of the complexity of an actual SoC, of the problem faced by an SoC design
So my experience in talking to hardware folks is that from their perspective, this doesn't look like that much big of a deal because they can see that, oh, okay, it's not that complex. All it's doing is actually this. And you can just unwind it in that way, right? And they also tend to have a view that software is a little bit magic or like infinitely adaptable is probably a better way to express that, right? Is that, well, you can just undo this in software, right? We're just going to tell you that this is mapping. You just got to know not to do that, right? And I have a feeling that they tend to underestimate the level of complexity that they are introducing for the other folks. And I strongly suspect that we do the same in the other direction, right? That we end up asking for things in the semantics where we say, well, can't you just make it do this? And, well, yeah, in theory, but, right? So anyway, as I said, I'm not trying to reiterate all the arguments here. I'm just trying to give you the flavor of where the work went, right? So you define your nice equivalence relations between, and this is obviously what I wanted to do because I wanted to start talking about refinements and whatnot. But what I found was, like, looking back on it, one of the most important things that happened was that we were writing a paper and we needed to be able to write down a few of these things, right? So I came up with a little syntax to actually write this and try to make it as compact as possible. And the only thing I was optimizing for there is it's got to fit in a column, right, of a paper and be readable. But this was the bit that sort of students working on the projects latched onto, is they really liked this little syntax for writing the stuff down, right? And again, there's nothing particularly interesting about it, but they liked the idea that they could actually write down a concrete thing. And so they went off and started specifying stuff, right? And this is where I've picked this one as the first of my stories, because this is the one with the happiest ending, right? Even though it's a bit windy on the way, is that, yes, students went off and started looking for things to specify. And so one chap, this was Reto, he, a very good student, he went off and found all the docs for the MIPS TLB. The MIPS R4600 TLB. And for anybody who knows a little bit about the history of architecture, is a very influential chip and very famously had a bug in its TLB, right? That if you ever installed two overlapping mappings on early revisions of this chip, you would actually kill it. That you could physically damage the hardware by failing to follow the specification, right? Because there were two wires that would just, one would try to drive it high, one would try to drive it low, and boom, dead, okay? So that's why that one was interesting. And yeah, so we managed to specify the thing. I won't bore you with the details, but then managed to show a nice data refinement that you lift from the actual state of the TLB up to a decoding net. And you show that, yeah, replacing an entry in the abstract side is equivalent to the write operation in the TLB. And moreover, he was able to go off and show that this equivalence relation I talked about before held between, on the left, a processor with an infinitely large TLB, and on the right, a processor with an actual small TLB plus a page table walker that walked through the decoding net node. So this was very cool, right? So this gave us some hope and that people were actually accepting papers on this. So this was good. Oh, right, that's right. And yes, and the thing that that reviewers want to know when you specify something, right, is like, how many bugs did you find? So, okay, this is like a 40-year-old chip. But, and again, the students feel happy if they find a bug. They go, yes, I found a bug. And yes?
So you said the old version contained the bug, so did you try to do the same proof for the old one?
Well, this is the old one. It's broke, like that version of the, I mean, there was no new version, right? This was a particular version of the MIPS chip. Okay. If you programmed it a certain way, you would kill it, right?
Do you see that in your model, or is it just a physical thing?
No, you can't. That's just the way it was an associative lookup, right? And these things are super expensive, and so they cut corners. And one of them is that they just literally wired the output of two gates together, not through another gate, right? What we can do is write down the requirement, right? What you have to do to avoid ever killing it. That's written in the spec of the chip, right? And that comes up in a few places. But anyway, the first bug was that you can do two things that conflict with each other. It says that, you know, it'll never overwrite a wired entry, but write random will always write where the pointer is currently pointing. These two things can't be true at the same time if you wire the entire TLB. That's like you fix it, you prevent replacements. It's not all that interesting. Students get very excited, as I said, when they find bugs. Put pictures like this up. This one was slightly more interesting. And this was just that, as specified, the boot up state of the chip allowed the bug to already occur, right? The contents of all entries were unspecified. This sort of overlapping entries things would happen. That's not really what I want to talk about so much as how we eventually actually got something sort of published on this that was a little bit useful. I said, okay, we've got this nice model, seems to work for a lot of real hardware. How would you write an operating system that actually had to live in this world, right? And so as I said before, I was working on the Barrelfish operating system at the time. And so if you don't know, I think I mentioned this already about 10 minutes ago, but Barrelfish takes multiple copies of a little microkernel, which is quite similar to SEL4. And most importantly for what we're talking about is that it has essentially the same object capability system. So all invocations, mapping, unmapping, whatever you do, are done by invoking a capability you have, right? And so we thought, well, okay, if you want to actually express the authority that's going on in here so that maybe you can say, okay, I want to be able to prove that this thing over here can't diddle around with my mappings down here and make me write something insecure. And what we came up with is the idea that you've got to split the authority to map a page into two parts. One page from one address space to another. One is the right to actually modify the source address space, which we called the map right. You know, my right to actually change what your virtual address points to. The other is the right to actually give you access to some piece of hardware by mapping it into your address space. And that was the grant right. And so we're able to pull these two rights apart and come up with a nice clean model with a nice capability system in Barrelfish. And so, you know, we actually made the whole thing work. You could run benchmarks on it. It actually did this whole thing. We wrote up a paper for, I think it was OSDI. And then we said, okay, well, all right, so these folks like Linux a bit, so let's, you know, point in that direction. We said, okay, and if you were to do it in Linux, you know, here's sort of how you'd have to go about it. You know, we haven't implemented this, but here are the steps you'd have to take. So reviews came back and said, okay, no, this looks like an interesting idea, but it seems that the Linux implementation is complete, and so we can't evaluate this yet. We had a complete implementation of Barrelfish. The whole thing worked, but it wasn't in Linux. This was apparently a problem. And this is not just me bitching about my papers getting rejected, right? Because we all like to do that. But it's actually, there was a lesson there, and that was about meeting people where they are, right? So particularly on the OS side, even though we've got these two conferences, you know, operating system design and implementation, the Symposium on Operating System Principles, the two big systems conferences. The operating system there, these days, in practice, it means Linux, right? This is the How to Make Linux Go Faster conference. Sadly. So, all right, we took that on board, and what we actually did was we went back and we submitted another version of the paper where we lied, right? We said, okay, we are proposing a new mechanism that leverages existing Unix functionality that you're all familiar with, right? You all know what mmap is. You can map things into people's address spaces, right? Well, we've got mmap X. And hey, it has this idea where you split the grant authority from the map authority. And then you map these things into each other. And here's how it looks like in the Unix file system, right? There's like this device structure down here that exposes the rights of every part of every ACID, every address space, each process ID. And then you use the file system permissions to control who gets access to this. And of course, what we're doing is rebuilding capabilities on top of the Unix file system. And yeah, they loved it, right? So yeah, awesome, well done. This wasn't implemented, by the way. We just described the interface. That was enough for people to love it. But nevertheless, I was sort of happy with there's a build in here. This is what happens when you just steal all your student slides to put together a retrospective, is that you forget what they had in them. So, despite the sort of the troubles we had convincing people initially, when we did what we thought was the clean model, this does sort of have a happy ending. This is a wonderful diagram that I'm not going to zoom in on for you, but this is I asked one of the students, do you have a list of sort of the stuff we published on this, And she came back with me, oh yes, I've got this kind of thing, and this is all the different publications over the years, and the X's are the rejections, and the master's thesis. This is a testament to the ingenuity and the work ethic of a PhD student who has a dissertation to avoid. Yeah, I saw Ben look at Peter. I saw that. All right. So that was mmapx. And I think in the interest of time, I will do one more. And this was the sad story, okay? I had another slightly happier one at the end, but this will do. All right. So this one is about circular buffers. And a lot of the things we're talking about here are about spotting common patterns in system design and trying to inject a bit of formalism into them. So what you see here is an excerpt from the manual of the Intel 82599. What that is a 10 gigabit Ethernet card. And what this is describing is the ring buffer structure where you give it descriptors to tell it where the next packet is, right? And the interesting thing about this is that this is accessed simultaneously from the CPU and the device. So this is fully concurrent. This is lock-free. And the interaction between these things happens by incrementing pointers, head and tail pointers. So the hardware gives you a way to atomically increment the pointers. And on top of that, you build this lock-free data structure, which is actually quite cool. And this is how they actually work. This is how you talk to these cards, okay? I thought, okay, and because one of the students had been working on a lot on high-performance networking and had seen this stuff. But it turns out this pattern pops up all over the place, particularly, for example, VirtIO, right? This is essentially the same thing VirtIO is doing, except between two CPUs, not CPU and hardware. There are a few differences here and there, but fundamentally, these are all doing the same thing, right? And bugs, important bugs, happen because of people misunderstanding the semantics and the invariance. The most important thing that happened is things like people modifying the memory after they've already given it away, or modifying it before they've actually gotten it, because what you're doing is you're passing back pointers to these buffers, these descriptors. That's what the descriptors are, right? There's the pointer to the buffer. And when can I start writing the buffer? And this turns out to be tricky to get right in all the cases, right? So looks like a case for some sort of formalization may be useful, right? And so the first thing, right, was to sort of, okay, can we unify this interface? And here you can already see the first mistake, right? Don't look at the details, that's not what the mistake is. The mistake here is that this slide exists, right? Is that the starting point was, here's a set of C prototypes, is the interface, right? Yes, that is the way to get somebody writing C doing it, right? But once you write it down so clearly, you run the risk, and partly this is my fault, that somebody who is used to writing a lot of C code will go off and start thinking in terms of these, right? And not in terms of the model. The model that I had been trying to push, and this is not by any means entirely my work, I was sort of doing the formal part, was to really nail down what ownership meant in this situation and when it's transferred, right? So we came up with a few ideas, you know, some principles of ownership, and then transferred these down into some invariants. And these are super, super simple, right? I mean, all these are saying is that you can't both own the thing, right? And you end up with a few additional sets because, of course, the actual transfer is not atomic, right? You stick something in the queue and it's not really mine anymore, but it's not really yours yet until you've popped it off. So you end up with these in-transfer sets, and you've got the pairwise intersections are empty. And this actually turns out to be a sufficient invariant for the entire thing, once you've got the right lifting function from the actual state. It's really nice, and it turns out to be a real invariant, as in it's literally true at every step of the concurrent execution, right? So this is the nice version, where you just show the invariant everywhere, and that's it. You've got no more interference proofs to worry about, no rely guarantee. And then the model operations are what you'd expect them to be, you know. Ignore register and deregister, they're details of something else. The NQ and DQ are the ones you care about. Comes out of my ownership set, goes into the transfer set, and vice versa, right? And then you can come up with this nice model where these sort of C methods correspond to transitions in this abstract state machine. And then you get to this wonderful diagram, which I liked, but everybody else thought was too busy, which expresses the refinement. We were able to show a real data refinement here that held under full lock-free concurrency, right? We had a sort of an intuition for ownership that was simple enough that, yes, the people who'd never done any formal methods were just doing engineering, really got it and were able to program to it. We could show the whole thing. In the middle, you've got, you know, a schematic version of this ring buffer where you've got your pointers into various places. On the outside, you've got that abstract transition system I showed you before. And in here, you've got a sort of a feel for what these are guarded transitions, when these things can occur, and then what the abstract operation corresponding to it is. And the really interesting bit here, and this is what the actual text around this originally showed, was that what makes it work is really carefully defining these. These are the lifting functions, right? Is that you need to take, all right, this queue from the head but up to, but not including the tail. This one should be from the reclaim pointer down to, but not including done, and like exactly the boundary conditions. Getting these right, that's what made it work, okay? So again, the details of this, while I like them and I would love to just talk your ears off about them, is not exactly the point, just that you believe me that yes, this worked on a formal level, we could really do proper concurrency proofs. And then we hoped to be able to go further and actually derive where your barriers would be needed. Again, I'm not going to explain this slide. This was something we hoped to be able to do, but didn't work. And the reason we didn't get to it, right, is that, again, I started by talking about the C interface, right? And what I failed to do was to really advocate for the fact that we needed to be always keeping the model in mind. So what happened is you had some PhD students who needed to graduate and needed to get a paper, and they wanted to publish in systems venues. And so to publish in a systems venue, you've got to have things like this, right? You've got to have number go up graph somewhere at the end for your evaluation. And so this is where the bulk of the effort went. And that verification, so actually completing that verification down to C, which is the thing that would have let us actually claim we have a fully verified XYZ, kind of didn't get finished because the effort got siphoned off into improving the performance of the thing. So all that nice sort of theoretical stuff, and it really was like, I quite like it. Like I'm really sour about this one because I liked the formalism. It was lovely and simple. It really worked out very, very cleanly. Like that invariant I showed you really was the actual invariant. But we weren't able to get all the way down to the finished proof that you needed to get it published because of the realities of people having to do engineering work and get a PhD in a more engineering, directly engineering focused discipline. That they pushed for this, and in the end, we didn't get a paper published in any case. Yes. So this is. I'm just gonna I'm almost finished, and so I will. I'm not. This is the last slide. Okay. So you're not gonna lose your chance. Okay. And so, yeah. So I had a third one to talk about, but clearly I think it's best if I leave it at this one. But you've had sort of a happy story of something that worked, and a story that didn't work out. And again, I take ownership of some of the failures here. And I think in both cases, there's a case to be made that the success and the failure hinged not on the technical merits of the things, right? But more the social issues, right? The social interactions, which I wasn't as effective at managing as I probably should have been. But yes.
So, that didn't sound too terrible to me. It sounded, bad for you, you didn't get your paper published. I was imagining when you said, oh, we gave this C interface out that someone would have built something that was broken.
Oh, right. Well, this is I'm an academic, right? So nobody builds a real thing. And successful failure is, do I get a paper out of it? And do I get to keep my job?
So I guess my question really is, was the thing that was built, do you believe that it actually...
Yes. Yes, I do believe that the thing they built was correct. Yes. Because these are good. These folks were really good at what they did, right? The systems people doing kernel hacking tend to actually have a very good intuitive understanding of a lot of this stuff. And they very often get it right. It's just that we didn't finish joining up the dots sufficiently to be able to claim, plant our flag. That was sort of the failure there. But then again, a lot of the folks have gone off to actually do formal methods stuff, right? And one of the things that actually made some of this work at all is I think the students who are most receptive and actually, some of whom have gone off to do additional verification projects on their own since graduating, were ones that actually took my course on formal methods. I taught a slightly offbeat course called Informal Methods. Anybody who knows Carol Morgan might have encountered the name before. But students seemed to like it, and it seemed to be very effective at encouraging people into, this is a good idea, this is fun, you want to do this. It is a completely non-scalable course. I can teach it up to maybe 30 students, and beyond that, it doesn't scale. It's way too interactive and question-focused. It works really well for small groups. Yes, Peter.
If you had had another few weeks or months with those students, was there scope for the formalization to help them make the numbers go?
So this is one of the things we were hoping for when I flashed out that slide about barriers. That was the hope there, is that it would allow you to be really clear about when you needed synchronization, because that gets really expensive. So I can't give an absolute answer to that, but I was hopeful that that would have been the case. And it was not so much not having the extra time, it was that in practice, I was working with somebody else's students, right? I am not a professor, right? They were not actually on paper my students. And so I didn't have the authority to tell them, no, you need to do it this way. Everything I've done over the past sort of 10 years has been by persuasion. I have had no force that I've been able to apply.
That applies.
I know it applies to official supervisors as well. Yes.
Further on the academic process, this is not a consolation, but it is also a fact that the reviewer too also believes that all testing and proof should be done on the entire Linux kernel.
Yes. I know. I think Ben was first and then Alistair. Yeah.
Isn't so much a question, but more of an observation. One of the lessons you haven't really brought out from that first story is that you made the specification language and it was good enough so people just started using it.
Yes.
And is there something to be learned there?
Well, I mean, I think yes, but to some extent, I think that lesson has already been learned, right? Like a few other people, I mean, in particular, I mean, Alistair had his hand up, right? There's like, you give people a language they see some value in, they take it and they run with it, right? I mean, to some extent, I've gone back and sort of pulled that one out to sort of jump on the train and say, hey, yeah, I did this too, right? I had this insight too. Whether or not that's really honest, right? But yes, I think there was definitely an element of that at play. But I don't want to claim to have had that insight.
But do you know if there was the language or what made them think enough to use it? Or is it just...
Yeah, I mean, it's the fact that they could actually write down real things. Yes, that's why people started actually specifying things. So the existence of the language, as opposed to I have to write all my stuff in Isabelle, yeah, is huge. Yes. Why a PhD student who is now about to graduate started by doing his master's thesis on writing a parser for this language. And ended up saying, hey, yeah, this is cool. And I'm going to go off and work on trustworthy BMCs. That's Daniel Schwinn, who you've met. Yeah, so I think, Alistair?
Yeah, so when you talked about proof about CleanQ, the proofs
Yes.
you wanted to do, I think you were talking about proofs that the software was correct. I wondered if you thought at all about if you'd had access to the things you'd need, would you be able to use that spec with the hardware?
I have had a dream of being able to do this, right? I would love to be able to do this. And I think the answer is yes. Yes, we did think about that. And the way the invariants are phrased are very much just on this operational model, right? Where you've got the atomic transitions, which are incrementing the pointers or reading and, and then you've got the non-atomic reading and writing to memory, and then you've got the barriers in the appropriate places. And that is essentially the same semantics the device sees. It's reading or writing the memory over PCIe, which is slightly different behavior, but not that different, right? It is effectively working like a core. So yes, I think it would apply.
I guess.
Yeah, and
One last question.
45 seconds if anybody's interested. Otherwise, we can chat in the break. I'm more than happy.
Excellent, cool. Thank you so much.